Dear friends, in Rabi chapter here, would like to welcome you to learn statistics, watching videos of the lecture series related to teaching learning activities in mathematics and statistics. In the previous videos, we discussed binomial, normal, and inverse normal distributions. Today in this video, I would like to discuss sampling distribution.
In statistics, as well as in data analysis, one of the fundamental concepts to understand is the sampling distribution. It plays a vital role in making inferences about population parameters based on the data collected from the sample. Also, it serves as a bridge between the data we collect from a sample and the inferences that we want to draw about the entire population. As you know, a sample is a subset of population. A sampling distribution is a probability distribution of a statistic obtained through a large number of samples drawn from a specific population. It is believed that the shape of the sampling distribution of sample means will approach that of a normal distribution, regardless of the shape of the parent population distribution. The larger the sample size, the better the normal approximation. This is the process of sampling distribution, shown here in this diagram. This process starts here from the population data, which has the distribution with mean mu and standard deviation sigma, having varied shapes such as skewed, uniform, symmetric, etc. From this population, we collect a sample of size n and find its sample mean, as shown sequentially in this diagram. If we continue taking sample of size n and find sample mean for each sample until all the possible samples have been selected, then the distribution created shown here from the means of these samples is known as the sampling distribution of the sample mean, which is approximately normal. Let's assume that the mean and the standard deviation of this sampling distribution be mu suffix x bar and sigma suffix x bar respectively. The relationship between the parameters of the population distribution and the sampling distribution is given here, which states population means of both the distributions are equal, but the sampling standard deviation equals the ratio of population standard deviation to the square root of the sample size. So far, we discussed principle and process of sampling distribution. Now let's proceed to sample data from different population distributions having varied shape to create sampling distribution. First, the normal population with mean 35 and standard deviation 15. We consider 1,000 data points from this distribution as shown here in this R console. This is population data. This is the histogram overlaid with this smooth normal curve of the population data is the distribution of the normal population, which is symmetric in nature. And also, this is a source of sample data. Let's start drawing samples of size 50 from this population. In the process of drawing samples, we compute sample mean of the selected sample each time. We repeat this process 10,000 times. That gets 10,000 sample means. This is the R code that generates 10,000 samples. The histogram superimposed with a smooth curve shown here is the distribution of the 10,000 sample means called sampling distribution, which is approximately normal. We know that the population parameters are mean mu equal to 35 and standard deviation sigma is equal to 15. Let's compute the mean and standard deviation of this sampling distribution. That is the mean and the standard deviation of 10,000 sample means. These are given here. Mu x bar equals 34.93 and sigma x bar equals 2.18. Regarding the relationship, we see that population mean is approximately equal to the mean of the sampling distribution. But standard deviation of the sampling distribution is not equal to the standard deviation of the population. If we compute simple math here, that is the ratio of population standard deviation to the square root of the sample size, we get this number as 2.12, which is approximately equal to this standard deviation of the sampling distribution. This satisfies the relationship that we discussed earlier. We shall consider chi-square population with 4 degrees of freedom. We also consider 1,000 data points from this distribution as well, which is shown here in this R console. This is population data from chi-square distribution. This is the histogram overlaid with smooth theoretical chi-square curve. This is the chi-square population distribution, a source of sample data. We observe the figure here that the distribution is right skewed. Let's start drawing sample of size 50 from this skewed population. As we go on sampling, each time we compute the sample mean of the selected sample. We repeat this process for 5,000 times. That gets 5,000 sample means. The histogram superimposed with a smooth curve here is distribution of those 5,000 sample means, called sampling distribution of the sample means, which is approximately normal. That we can see the bell curve here. Samples has been drawn from the chi-square population with 4 degrees of freedom. So it has mean equals 4 and the variance equals 8. So the standard deviation of this distribution equals square root of 8, that is 2.83. Hence the population parameter are mean equals 4 and standard deviation equals 2.83. Let's compute the mean and standard deviation of this sampling distribution. That is the mean and standard deviation of the 5,000 sample means. Those are mu suffix x bar is 4. The standard deviation sigma x bar equals 0.4. Regarding the relationship, the mean of the sampling distribution is exactly equal to the population mean. Both are equal to 4. And standard deviation of the sampling distribution is not equal to the population standard deviation. But the standard deviation of the sampling distribution is equal to the ratio of the population standard deviation divided by the square root of the sample size. Last but not the least, the sampling distribution is normal regardless of the skewed population. Next, the population distribution we consider here to sample data is the right skewed exponential distribution with the rate parameter 10 and the population size 1,000. This histogram overlaid with theoretical exponential curve represents the exponential population distribution, a source of sample data. We start drawing samples of size 50 from this skewed population distribution and compute the sample mean for each sample. This sampling process is repeated 5,000 times, getting total of 5,000 sample means. This histogram superimposed with a smooth curve shown here is the distribution of the sample means, popularly known as the sampling distribution of the sample means. The smooth curve looks like a bell curve implies that the sampling distribution is approximately none. This sample data comes from the exponential population with rate parameter equals 10. Equivalently, the mean and the variance of this distribution is 0.1 and 0.01 respectively. Naturally, the standard deviation of this distribution is 0.1. Hence, the population parameters are mean equals 0.1 and the standard deviation equals 0.1. Let's compute the mean and standard deviation of this sampling distribution. That is the mean and standard deviation of the 5,000 sample means. These are mean equals 0.1 and standard deviation equals 0.03. Regarding the relationship, mean of the sampling distribution is exactly equal to the population mean, but the standard deviation of the sampling distribution is not equal to population standard deviation, but it is approximately equal to the ratio of the population standard deviation to the square root of the sample size. This satisfies the relationship that we discussed earlier. Finally, the sampling distribution is approximately normal regardless of the skewed population. Now we shall consider some real-time problems related to sampling distribution that we come across in our day-to-day activities. The first example, here we have a normal distribution with mean 20 and standard deviation 2.5. This is the graphical display of this problem. In the first part of this problem, we shall find the probability as in usual normal distribution that a randomly selected element x exceeds 22. By using this R command, we get the probability of this event as 0.2112. In the second part, we shall find the mean and standard deviation of the sampling distribution that we create from this distribution with the sample size of 9. We find the mean is 20, same as the mean of the population distribution, but the standard deviation is 0.833. That is the ratio of the population standard deviation to the square root of the sample size. In the third part of this problem, we shall find the same probability as in the first part, but considering the sampling distribution. That is the probability of x bar greater than 22. That is with the change standard deviation 0.833. We could see here that this probability of the sampling distribution differs significantly with the similar probability in the population distribution in part 1. In this second example, we consider similar problem, but the probability towards the left tail of the distribution. The problem states that the mean lifetime of an automobile battery is 60 months with a standard deviation of 15 months. This is the graphical display of the population distribution and the population parameters of the problem that is shown here. Here we are trying to find out the probability that the lifetime of the battery is less than 55 months. But the question has two parts. The first part of the problem requires the simple probability that a randomly selected battery has lifetime less than 55 months. Whereas in the second part, we need to find the probability of mean life of the battery less than 55 months, considering the sample size 36. For the first part, let's define a random variable x that counts the lifetime of a battery in months. Here we shall try to find out the probability given by this expression, that is the probability that a random variable x is less than 55, as shown here in the first graph on the display. The R solution is given here. Copy this R command and paste at this R console. We get the solution here, 0.369441. That is about 37% of the batteries have a lifetime less than 55 months. To solve this part C, we need to create the sampling distribution as shown here in this middle graph. That is a distribution which has the mean as the population mean, but the standard deviation is the ratio of the population standard deviation divided by the square root of the sample size. Here the sampling distribution has the mean equal to 60 months and the standard deviation equal to 2.5 months. Let's define x bar is the random variable that counts the mean lifetime of the battery in months. We are interested in finding the probability of mean lifetime of a randomly selected battery in this sampling distribution be less than 55 months. We shall find the probability given by this expression. That is the probability of x bar less than 55. The R solution is given here. Copy this R command and paste at the R console. Here we get the answer 0.02275,013. That is about 2.28% of the batteries has mean lifetime less than 55 months. Here in this example, we have the distribution of the score in a skill evaluation test, having mean equals 1820 and the standard deviation equals 550 points. From this distribution, a sample size of 225 tests is considered for sampling distribution. This is the graphical display of the population distribution of the problem that is shown here. Here, we shall focus on the event that the mean of the sample would differ from the population mean by less than 50 points. This phrase can be expressed mathematically in this form. That is, the absolute value of the difference between sample and population mean is less than 50. We shall discuss here how to find the probability of this event. That is, the probability of this absolute difference is less than 50. With a mean value of 1820, this expression becomes this. That is, the probability of absolute difference between the sample mean and 1820 is less than 50. If we solve this absolute value equation, we get this solution. That is, the sample mean lies between 1770 and 1870. Hence, the probability of this expression is same as the probability of this solution. For this probability, our solution is given here. So if we copy this R command and paste at this R console, we get this result 0.827279. That is about 83% of the score values lies between 1770 and 1870. That is within 50 points of the mean. Here, this example mentions the distribution of per capita consumption of milk per year with a mean of 150 liters and a standard deviation of 30 liters. From this distribution, a sample of 36 people consuming milk is considered for sampling distribution. This is the graphical display of the population distribution of the problem shown here, and also the population parameter as well as the parameters of the sampling distribution. Here, we shall focus on the event. The sample mean would differ from the true mean by more than 8.5 liters. This phrase can be expressed in mathematical form as this. That is, absolute value of the difference between sample and population mean is greater than 8.5. We shall discuss how to find the probability of this event. That is, the probability of this absolute difference greater than 8.5. That is, the probability of this absolute difference greater than 8.5. Replacing the population mean by the given value 150, this expression becomes probability of the absolute difference between the sample mean and 150 is greater than 8.5. If we solve this absolute value equation, that is the absolute value of the difference greater than 8.5, we get this solution as sample mean less than 140.5 or sample mean greater than 158.5. Hence, the probability of this expression is same as probability of this solution, which equals the sum of the extreme left and right tail probabilities given by this expression. The R solution for each of these tail probabilities is given here. If we copy this command, left tail probability, and paste at this R console, we get this solution. Similarly, if we copy the command for the right tail probability and paste at this R console, we get the right tail probability. The probability of each of the tail is given here. The sum of these extreme probability is the solution of the problem. That is about 9% of the consumption of milk stay away of 8.5 from the mean. We discussed in detail the sampling distribution of the sample means, but we have other sample statistics such as sample variance, sample standard deviation, sample proportion, etc. as well. Each statistic would have its own sampling distribution that we shall discuss in our later videos.